So the plan for this video is to go over homework number 4, and I'm actually planning on doing this as a two-part video because most of the problems required using some kind of solver. So I'm going to do the second part of the video. I solved all of mine in MATLAB, but you could also use Polymath or Excel. So anyway, so for this part of the video, I'm planning on going through and setting up the problem up into the point of where you would put it in whatever program you're using to solve your equations. So for the first problem you were given, so problem number 1. For problem number 1, you were given concentrations at various times in a batch reactor and the concentrations, and you didn't need the Ca naught, so you were given concentrations at various times in a batch reactor, and it says determine the order of the reaction and the rate constant. So you're given Ca at different times. And this is a good thing to know how to do, because if you're running experiments in the lab, you're likely going to be measuring some kind of concentration with time. And so if you're trying to figure out what your order of reaction is and your rate constant, so then you can write a rate law, then this is a good thing to know how to do. So first of all, we're using a batch. So usually these experiments are done in batch reactors, and you're looking for a rate law. So you have data, you have Ca at various times. You want to take this and write a rate law. So I'm going to write down the equation for a rate law. So rate law, and that would be minus Ra is equal to Ka Ca alpha. What we're looking for is this Ka and alpha. And so we need to figure out a way to relate this to this so we can figure out what these are. So what we can do is look at if we plug this into the mole balance for a batch reactor, then we get minus dCA dt is equal to Ka Ca alpha. And then if we take the natural log of this, we get natural log minus dCA dt is equal to natural log Ka plus alpha natural log of Ca. So then if you look at this equation, you can see that this is actually the equation for a line. So if you look at y equals mx plus b, this would be mx and this would be b. So in other words, alpha, so your reaction order is the slope, and then ln of Ka, this is your y intercept. So what we can do is figure out, we have Ca and T at various times, and so we can figure out what the derivative is, the dCA dt. We already know Ca, so we can just take the natural log of it. And if we plot the natural log of dCA dt versus the natural log of Ca, then we should be able to get the slope and the y-intercept. So then we can get alpha and the rate constant. So the first thing you need to do for this problem is calculate dCA dt. So calculate dCA dt. And there are a few different ways you can do this. First of all, you can use graphical differentiation. You can use numerical, differentiation formulas. Or you can differentiate a polynomial. So these two you could, I mean, I don't recommend doing any of this. I don't recommend doing this by hand for this particular problem because you have quite a few data points. If you only had a few data points, like maybe 4 or 5, this would be pretty easy to do this one or this one by hand. But you would need to use a regression program to get your polynomial. So with this one, basically what you would do is plot your data, so CA and T. You would do a regression to get a polynomial, and then you can just take the derivative of it. And so I'll show you real quick well, okay, so first of all, taking a step back. So once you get dCA dt, then I already pointed out, so then you would just take the natural log of it and you would plot that versus the natural log of CA, and then you can get your slope. And then you would do a linear regression because you should have a straight line. I mean, this is the equation for a line. And then you can get your reaction order, or the rate order from the slope, and you can get the k constant from the y-intercept. So I'm going to show how to do the graphical differentiation on the board, but really I solved this from here on. I solved this problem in MATLAB. So what I did, I actually used all 3 of these in MATLAB, and so I was able to get dCA dt using all 3 methods, and then I just plotted this in MATLAB, did a linear regression, and then I was able to get the equation for this line. And so I'm going to show you how I did that in the second part of the video where I go over MATLAB. But right now I'm just going to erase some stuff real quick. The way you would do the graphical differentiation is you have t, and I'm just going to do this for a few data points because there's a ton, and I'm not planning on finishing the problem with this. I just want to kind of show you how it's done so you know how to do this by hand, in case, like, if you only have 4 or 5 data points, it might be faster to quickly do it by hand than to try and do this on the computer. So or if this shows up on an exam, then you might want to know how to do it by hand. So T, CA. So what I usually do when I'm doing the graphical differentiation is, first of all, I write down my data in this fashion. So for T, you have 0, 10, 20, 30, and for CA, for 0 it was 2.5, for 10 it was 1.47, for 20 it was 1.19, and for 30 it was 1.04. So the first step is to calculate delta CA over delta T. And so the way you do that is you take the second one in the series, so say this is, well, okay, so say this is CA1, CA2, CA3, and this is T1, T2, T3. So then this would be CA2 minus CA1 divided by T2 minus T1. So if you do that, you get 0.103. And then the next one would be CA3 minus CA2 divided by T3 minus T2. And if you do that, you get 0.028. And then this one would be Ca4 minus Ca3 divided by T4 minus T3, and that was 0.015. These numbers are so teeny, I actually ended up multiplying it by 100, so this would be minus delta Ca delta T multiplied by, actually I did 1,000, so 10 to the third. So then this one was 103, 28, and 15. And if you do something like this to make your numbers easier to plot, you just want to make sure that you take into account that factor when you finish solving your stuff. So then you would plot time here and dCA dt. So for time, you have 0, 10, 20, 30, 40, and then I'm just going to say, since my biggest number is 103, I'm just going to say the top is 100. So 50, 25. And what you would do, so my first one is 10 and it's 103, so I'm going to say that's about right here. So I have this, and then the next one goes to 20 and it's 28, so that goes here, and then the last one is 30 and that goes to 15, so that would be about right here. And so you can quickly see why doing this for this particular problem would be nearly impossible by hand, because almost right away you're going to get numbers so low that you can't graphically plot them very easily. I mean, if you're doing this on a computer, you could probably graphically plot it and see, but you might as well use one of these other methods if you're going to do it on the computer. So then you would draw like a curve that passes roughly through the center of each of these. And that's probably not a very good curve, but what you would do is then this spot, so this was 103 right here, and I mean this scale is really bad, so that's probably something like, I don't know, 110. So then you could say dCA dt is whatever this point is would be the first one, so if I just say that's 110, and then the next point would be this one, so say that's like 60 or something. And I mean, obviously if you were doing this for real, you would want to be a lot more careful about how you draw this and read these off. This is kind of a bad drawing, but I'm just doing this to show you how it's done. So then next one would be 24, and then this one, and whatever that is. So you can see if you're doing this by hand, you want to be pretty careful about how you draw your plot, and you also need to have data that is fairly evenly distributed. Otherwise you're not going to be able to do this in a reasonable way, because for instance with the data we have for this problem, you end up with a few big numbers, and then most of them are really teeny, so there's no way you would be able to draw this and then draw reasonable curves. So that's why this problem was best done on the computer, and so I'll finish this problem in the second part of the video in MATLAB. Alright, so for problem number 2, it says you have concentration of sucrose as it is hydrolyzed as provided in the table below. So once again you have a time and you have a concentration, so you have a concentration that you're measuring with time. And you know that the rate is modeled by the Michelis-Menton kinetics, so it gives you this minus RA is equal to 0.01 K Ca over Ca plus m. And then you're given concentration per time. And it says find K and M, so we're looking for K using an integral method and by employing nonlinear parameter estimation. So there are a couple ways you can find your constants for your rate parameter from data. And the first one is the one I just talked about with the first problem. And then the integral method is another method you can use. And so the integral method is normally only used if you know what the order of your reaction is. And the reason why you want to know the order of your reaction if you're using that method is because you're going to spend a lot of time just guessing what it is and then plotting things and seeing if it works. And then if it doesn't, you have to guess again. And so I feel like it's easier to use the other methods if you don't know the rate order. But if you do know, like in this case, we know what the rate law looks like, then the integral method is a pretty good one to use. So the way this works is, first of all, we want to write down our mole balance for a batch reactor because we're assuming all of these whenever you're getting data like this, it's almost always done in a batch reactor, so I'm just making that assumption. So batch. So first of all, you want to write down the mole balance for a batch reactor, and that is dCA dt is equal to Ra. And then we know what Ra is, so minus Ra is equal to 0.01 K Ca over Ca plus m. And then we want to put this in this form. So we want minus Ra to be equal to K1 Ca over 1 plus K2 Ca. So we can do that if we can figure out what K1 and K2 need to equal to get this equation. First of all, what we can do is divide through the m, because this is 1 plus K2 over Ca. So if we do that, we get minus Ra is equal to 0.01 K Ca over m, and that's over 1 plus Ca over m. So then we know that K1 is equal to 0.01 K over m, and K2 is equal to 1 over m. So then we can take this and plug it in there. So if we do that, we get dCA dt is equal to K1 Ca over 1 plus K2 Ca. And then we want to integrate this. We want to separate and integrate. So if we do that, we have 0 to t dt is equal to Ca naught to Ca, because remember we're solving this in terms of concentration instead of conversion. So most of the problems we've been doing up until now, we've been using conversion, so it's been 0 to x, but that's why these limits are what they are. We don't have x in this equation. So 1 plus K2 Ca over K1 Ca d Ca. And then if we integrate this, we get t is equal to the natural log Ca naught over Ca plus K2 Ca naught minus Ca over K1. And what we want to do with this equation is we want to rearrange it so it looks like the equation for a line. So we want it to look like y equals mx plus b. Because the way the integral method works is you guess what you guess what your rate law looks like what the order is. Go through, integrate, and then plot it, and if you have a straight line then you know that it was right, but if you don't then you know that it was wrong, so you have to go back and guess a different order. So I'm going to erase some stuff real quick. So then if we rearrange this equation so it looks like a straight line, we want to plot the appropriate function of Ca versus time. So if we rearrange this into something that we can plot, then we get the natural log of Ca naught over Ca over Ca naught minus Ca is equal to K1t over Ca naught minus Ca minus K2. So then you can see if I write y equals mx plus b, first of all, K2 is, well, negative K2 is b, so negative K2 equals b, and m, well, K1, well, and then when I plot this, I'm going to divide through the, I'm going to divide t by the Ca naught minus Ca, so that accounts for them. So then K1 is just equal to m. And then we can solve for the k and m in this equation because we know that K1, so this is equal to 1 over m, and this one is equal to 0.1 k over m. So then, so I'm going to finish this problem in the second part of the video in MATLAB, but all I did was plot this. So I took the natural log of Ca naught over Ca divided by this. So I plotted this versus t over Ca naught minus Ca, and I got a straight line, and then I used linear regression to figure out what the equation was for the straight line. So then I got the y-intercept and the slope from that. So then you should be able to get these. So for number 3, you once again have concentrations with time, and so 3, and we have t a bunch of times, Ca bunch of concentrations, and it says determine the reaction order and rate constant. So this problem is actually identical to number 1, and you could use, so I actually solved this the same way as number 1, and so I'm not going to go through all the math again because it's the same, but it's basically the same method. Like you write down your rate and then you write down your, so, well, I guess I'll just write it down. So you write down your rate, so minus Ra equals K Ca alpha. So we're looking for K and alpha, so the reaction order and the rate constant. And then you would plug that into your mole balance, and you get this K Ca alpha. And then you take the natural log of this, so natural log minus dCa dt is equal to alpha ln of Ca plus ln Ka. So then this is comparable to a line. You have y equals mx plus b. So this is why your slope is alpha and b is the natural log of Ka. So then so the big part of this problem is actually figuring out what dCA dt is, and like I talked about, there's 3 different ways you can do that: the graphical differentiation, numerical differentiation formulas, or the differentiating a polynomial. And I'm going to go over how to do all that in MATLAB, and so I'm not going to go through that again. But so then once you know this, you take the natural log of it, plot it versus the natural log of Ca, and then you should get a straight line. And so then using linear regression, you can get the equation for a line, and then you know that the slope is alpha and b is the y-intercept. And then with this problem, theoretically you could also use the integral method, but I chose not to use the integral method for this problem because you're looking for the reaction order. You don't know what it is. And so if you use the integral method, you would have to guess what that is, and then separate and integrate this, and then plot it and see if you get a straight line. And if you do, then you know you guessed right, but if you don't, then you have to try and guess it again. And so I just feel like that takes I mean, if you guessed right the first time, it might be fast, but with this, I feel like with this other method, it's more just stepping through the steps of solving the problem with no guesswork. But this one involves doing the integral method might involve some guessing if you don't know what the reaction order is. So that's why with this one I did it the same way as number 1. And I'll go through that in the second part when I go through MATLAB. So number 4. Number 4 was a packed bed reactor with so you had to derive equations accounting for a pressure drop and without a pressure drop. So first of all, it says, so number 4, it says a second order reaction, so second order 2a plus b to c, says you have a PBR. The rate constant K is 10. And I'm going to write the units. I already went through all the units on this problem when I did it, and they all work out. So I'm not going to rewrite them on each step, but I'll just write the units here. So per kilogram catalyst per hour. The molar flow rate, so F A naught, is equal to 0.12 kilomole per meter cubed. The volumetric flow rate is 8 meters cubed per hour. And the weight of the catalyst is 30 kilograms, so W is 30. And it says, so this problem had 3 parts. So for part A, it said, derive an integrated equation relating the weight of the catalyst to conversion with and without pressure drop. And then for B, it says calculate the conversion without the pressure drop. And for C, it says determine the conversion with a pressure drop. And then it gives you alpha is equal to 0.04. So derive equation for W, and conversion with and without pressure drop. And then B, it says conversion without pressure drop, and C, conversion with pressure drop. Alright, so we want to do this problem like we've done all of them. First of all, you start out with a mole balance. So mole balance is FA naught dx dw is equal to minus RA prime. This is the mole balance for a PBR. And then rate law. We know it's second order, so minus RA prime equals K CA squared. And then for the stoichiometry, CA is equal to CA naught 1 minus x. And so one thing I'm doing with this problem is, since I need to get an integrated equation for the pressure drop, the only way to do that is to assume that epsilon is equal to 0. So I'm making that assumption. So that's why I have CA is equal to CA naught 1 minus x. And I'm not dividing it by the V naught 1 plus epsilon x, because I'm assuming that epsilon is equal to 0. So basically I'm assuming no volume change. And so the reason why I decided I needed to do that for this problem is because to get an integrated equation, the pressure drop, you normally end up with two coupled ODEs that you need to solve numerically. But if you assume that epsilon is equal to 0, then you can, and I'll go through the math, but you can convert your pressure drop, well, you can integrate your pressure drop equation and just get an algebraic expression without pressure drop. And so now I can combine and integrate, so I get FA naught dx dw is equal to K CA naught squared 1 minus x squared. And then FA naught is equal to CA naught V naught. I can separate and integrate this, and I'll get 0 to x dx over 1 minus x squared is equal to K CA naught squared over FA naught 0 to w dw. And so then if I integrate this, I end up with K CA naught squared multiplied by w over FA naught. I guess I didn't end up plugging that in, so, but you could, and then you could cancel out one of the CA naughts. So, and then this is x over 1 minus x. So this is what you get with no pressure drop. So now I'm going to erase some stuff and go through the one with the pressure drop. I'll rewrite for the pressure drop. I'll rewrite the mole balance and rate law and stoichiometry just so you can see where you account for the pressure drop. So this is with pressure drop, and so the mole balance is still the same, and that is FA naught dx over dw is equal to minus RA prime. The rate law is also the same. Minus RA prime is equal to K CA squared. And so where you see the change is in the stoichiometry. So with the pressure drop, we have CA is equal to CA naught 1 minus x y. So this is the difference. We multiply this by y, and y is equal to p over p naught. And if you're confused about this, then go back and watch the video I did on pressure drop, because I went through where this, like, why it's written like that. Then we can write an equation for the pressure drop. So pressure drop. So these are the two differences. We end up multiplying Ca by y. And if you remember, this P over P naught was always here. We've just been assuming it's 1, so that's why it goes away, because we've been assuming with no pressure drop, P over P naught is equal to 1. So then you need to leave this in to account for it now, and then we also need to write the equation for a pressure drop, which is dy dw is equal to minus alpha 1 plus epsilon x over 2y. And also, if you're confused about where this equation came from, then go back and watch that pressure drop video, because I went over it in pretty good detail. So normally you would just jump to like an ODE solver at this point, and you would solve. Oh, and the other thing is, when you're doing a pressure drop problem, you have to write your mole balance in differential form. So make sure you use this form of the equation and not the integral form. So normally at this point you would go to an ODE solver and you would solve. You have two coupled ODEs that you need to solve. But the problem statement is asking for an integrated solution, so an analytical solution. So the way you can do that is, we've already assumed that epsilon is equal to 0. So then I can say dy dw is equal to minus alpha over 2y. And so then I can separate and integrate this. And if I do that, so you separate and integrate this, and you want to say that y is equal to 1 when w is equal to 0. And if you do that, you get y equals 1 minus alpha w to the 1/2. And so then you can plug that equation in for y, and then you can just go through and do the same thing. So plug this into there, and you should be able to integrate that. So I'm going to erase some stuff real quick. And just make sure, like, if you're solving these problems, I mean, I would not jump straight to this equation unless you know for a fact it'll work. So this equation only works if you're, first of all, assuming that epsilon is equal to 0, and it also has to be isothermal. So I usually start with this equation, and then if you know that you're making these assumptions that epsilon is 0 and it's isothermal, then you can integrate this and get that. But you don't want to use this if it doesn't apply to what you're doing, because this is making some assumptions. And so it's better to start with this one where you're making less assumptions and then go from there. So anyway, if we combine all of this, then we get Fa naught dx dw is equal to k Ca naught squared 1 minus x squared, and that's all multiplied by 1 minus alpha w. And that's not squared because it was to the 1/2, and so when I squared it, it's just 1. So then I can separate and integrate, and so I get Fa naught k Ca naught squared 0 to x dx over 1 minus x squared equals 0 to w 1 minus alpha w dw. And so then if I solve this, I get Fa naught over k Ca naught squared x over 1 minus x is equal to w 1 minus alpha w over 2. So this is your equation for the pressure drop, assuming that epsilon is 0 and it's isothermal. And so then you have everything you need for B and C because you have the equation. So I'll just write down this equation again real quick that we derived for the first part. So this was with pressure drop, and then K Ca naught squared W over Fa naught is equal to X over 1 minus X. And this is no pressure drop. So you have your two equations and you're looking for the conversion. And so you should have everything you need. We know what K is. We know what Ca naught is because we can get it from Fa naught divided by B naught. We know W. We know Fa naught. So you should be able to solve this for X. And then this one, same thing. You know Fa naught. You can calculate Ca naught. You know K. You know W. And you know alpha. So you should be able to calculate X for that. Or you should be able to calculate the conversion. All right, so for number 5, as you have a gas phase reaction, so gas phase that's 2A to B, and it's taking place in a PBR. So I'm just going to keep saying this because like this is how I always do these problems. As I read the problem statement, I always write down the data as I'm reading it, because then you have a list of everything you were given, and then you can just go from there. You can just go through your stoichiometry, or not, sorry, you can go through your mole balance, rate law, stoichiometry, and just pull stuff off as you need it instead of having to keep going back to the problem statement. I don't know, I feel like this is, you're less likely to get confused doing it like this. So K is equal to 0.5 liter squared mole kilogram second. And then it says your initial molar concentration of A is 0.2 moles per liter. So Ca naught is equal to 0.2 moles per liter. The volumetric flow rate is 0.15 liters per second, so V naught equals 0.15 liters per second. The pressure drop parameter is 1, so alpha is equal to 1. And then it says, formulate the ODEs that describe conversion and pressure drop as a function of weight. As a function of weight of the catalyst. Solve the ODEs using an appropriate platform and find conversion and dimensionless pressure drop at the exit of the packed bed. And it says you have 1 kilogram of catalyst, so W is equal to 1. So you're looking for X and Y, because Y is your dimensionless pressure, so because Y is equal to P over P naught. And so this problem is pretty much identical to the last one. The only difference is you're not going to solve it by hand because you're not making an assumption about epsilon this time. So this time you need to solve the two coupled ODEs. So we do the exact same thing. We write the mole balance. So Fa naught dx dw is equal to minus Ra prime. Remember, since we have a pressure drop this time, we need to write this in the differential form. And then we do our rate law. And I'm just going to, it didn't say much about the rate law in the problem statement, so I'm just going to assume it's elementary. So I'm going to say minus RA is equal to K CA squared, because it's 2A to B. And then the stoichiometry is CA is equal to CA naught 1 minus X over 1 plus epsilon X Y. So this is so it's gas phase, and then we need to account for the pressure drop, so we can't say that Y equals 1. And then we need to do the pressure drop, and so that is dy dW is equal to minus alpha over 2y 1 plus epsilon x. So then at this point you would go to your solver, and I'm going to be using MATLAB in the second video, but you could also do this in Polymath or any solver you want. And so you would write a program to solve these two coupled ODEs, and then you would just put in all your parameters. So so these would just be variables. And so I'm going to go over how to do that in MATLAB in the second part of this video, but this is how you get all the equations to set up your problem. All right, so for number 6, it says you have a reaction that's A plus B to C plus D plus E. It's in a semi-batch. A solution containing 1.6 molar concentration of B is fed, so C B naught is equal to 1.6, is fed at a rate, so V naught of 0.12 moles per minute. And this was molar, so moles per liter. And to a reactor containing 1450 liters, so 1450 liters of 0.8 molar A. The reaction rate is 5 liters, and I actually said that was the rate constant, not the reaction rate, so K is equal to 5. And the reactor capacity is 2,400 liters, so V equals 2,400. And then it says write balances for all species and find plot concentrations of all species as a function of time. So mole balances on all species, and then plot. So I'm going to make plot of time versus CA, CB, CC, etc. It's easy to get flustered on problems like this where it looks different from what we've been doing, but this problem is still the same thing. First of all, you start with a mole balance, and then it says we're looking for a mole balance for all of the species. So instead of using we're using concentrations, because concentrations is what we're looking for, instead of conversions. So for each species, so for A, it would be dCA dt is equal to RA minus V naught over V CA. And if you aren't sure where this came from, then review semi-batch reactors. I did a video on how to derive these mole balances. And you don't need to rederive the mole balance every time, but you should know where these come from, so then you know how to do these balances. So dCB dt is equal to RB plus V naught CB naught minus CB over V dCB dt is equal to RC minus V naught C of C over V. Oh, this is dCC, concentration of C. And then dCD dt is equal to RD minus V naught CD over V, and dCE dt is equal to RE minus V naught CE over V. So we're doing the mole balance in terms of concentration instead of conversion, and so that's why we're doing a mole balance on each part of this reactor, so on each of the reactants and the products. So then we can just use stoichiometry to figure out what the rate laws are. So rate law, and so first of all, I just assumed that the rate law was elementary, so I said it was minus RA is equal to K CA CB. And then I said, using stoichiometry, we know that minus RB is equal to minus RA, RC is equal to minus RA, and this is also RD and RE are also equal to minus RA. Then at this point, I just plugged all of this into MATLAB and solved. So I just solved all of these couple differential equations, and so I'm gonna in the second part of this video I'm gonna go over how I did that. But you could also do this in Polymath or any other ODE solver you like to use. And so really you would just put in these equations, put in your rate law definitions, and then all your constants, and just solve and do your plots. So that's how you get the equations for this and set it up, and I'll go over how to solve everything in the second part of this video.